Alright, welcome back everybody. This is our fourth video in our playlist of a geometric series. So we'll take a look at the formula, what it means to be a geometric series. It's very similar to an arithmetic series, except we start with a geometric sequence and then start adding up the terms, which is where we get the series part of this. So there's your definition of it on the screen. Again, all the links of these resources will be in the description box. You can find them. So the sum of the terms in a geometric sequence, well, that is going to be your series. If you have a geometric sequence, add them up, you got a geometric series. So let's look at what the formula for this happens to be. So there's the pattern for your sum. So if you think about a geometric sequence, you have the first term, you multiply it by a common ratio, you get your second term, so on and so on and so on. So you keep on going. Now, if we take that sum formula and we multiply both sides of it by that common ratio, t1r plus t1r squared plus t1r cubed, and you keep on going all the way to the end, and you're going to end up with t1rn minus 2 plus, well, t1rn minus 1, well, times r again. If you just keep on going with this pattern, right? You've just included another ratio to this. I did it to both sides. And you can simplify this down below like you see there. Now, if you subtract the one you started with, the original sum formula, adding up the terms, and the one which we multiplied both sides by r, if you subtract them, things start to cancel out in between, and I'll even start crossing things out for you. You're going to see t1r's, t1r squareds, t1r cubes, all the way down. Things will cancel until you get to a point when all you're really left with is this. You're just going to be left with your first term minus, well, your first term times that ratio n times. Everything else will cancel. Now, if you factor both sides to reduce this a little bit, right, if you factor a greatest common factor out, on the left side here we can take out a factor of Sn, so we're left with 1 minus r. That's going to be equal to, well, if I factor out t1 on the right side, again, 1 minus r to the power of n. If you solve this for Sn to get your sum formula, or your sum variable by itself for your series, well, you could divide both sides by that 1 minus r to isolate your Sn variable, so that Sn is equal to t1, 1 minus r to the power of n, whole thing divided by 1 minus r. And that is a formula you can use for a geometric series to find the sum of the first n terms. It will work for any geometric series that you may encounter. So that is all fine and good, but what happens if that r value is equal to 1, right? Think about what happens if r is 1. Well, if r is 1, I'll leave the formula there, so if r is equal to 1, then the ratio is 1, which means each term is equal to the last. Remember how to find a common ratio. You could take t2 and divide it by t1 to get r, but if they are the same, right, if your ratio is 1, that means t2 and t1 have to be the same thing, right, which means t3 divided by t2 will also give you 1. They're identical, right? The terms have to be the same. So not super interesting because the terms are the same. Why can r not equal to 1? Well, think about the denominator of your formula, right? R can't be 1 because if it is, then you get a denominator of 0, which is a problem, right? We can't divide by 0. Right? We can't divide by 0. Right? That causes a problem for us mathematically, so I can't do it. Okay, so there's a formula that will work for us, and another way of writing this formula can be achieved by factoring out a minus. Essentially, we can switch these two terms around, take a negative out of each of them, and cancel it out. So the other way that you could see this is the sum of n terms is equal to the first term. I'll switch these two terms around on the inside. Right? If I reverse them, maybe I'll write the extra step here. Sorry, let me erase this. If I factor out a negative sign, that means this becomes a negative 1 plus r to the power n over that negative sign, again, negative 1 plus r. Essentially, these get reversed. This is essentially what's happening. A negative comes out of each of them, but those negatives are going to cancel, right? They'll disappear, and I can rearrange the terms in the brackets because addition can happen in any order. So this works out to be t1 rn minus 1, and on the bottom, r minus 1. So same thing, works the same way, except, well, the terms are just reversed. It doesn't really change anything. It's more of a personal preference at this point. So let's say we can use this formula to do some things. So that first example says, find the sum of the first 12 terms of this series. So if I just zoom in a little bit, we know a couple things here. I know the first term is 1 over 4. I know the ratio is 2. And so I write down my formula again, the sum of the first n terms of a geometric sequence. I need the first term, rn minus 1, and then r minus 1. So if I have the first term, that's good. I know I'm looking for 12, so I also know that n is 12. I just need the sum of those 12 terms, so I've got everything I need. So the sum of the first 12 terms is our first term of 1 over 4. My ratio is 2, n is 12. We'll subtract 1, and then on the bottom, 2 minus 1, which will simplify to 1, so that's kind of nice. So this works out to be the sum of our 12 terms will be 1 over 4. 2 to the power of 12 is something I need. So 2 to the power 12 works out to be 4096. And then minus 1 is there. Underneath, well, my 2 minus 1 will just disappear because it works out to be 1, so I don't really need it, but we can include it for completeness sake. And then I just need my calculator. So I'll subtract 1 from my 4096, multiply it by 1 over 4. So let's just divide it by 4. And we'll see we get a decimal. So let's turn that into a fraction by pressing math 1, and we'll leave it as an exact value here. So the sum of the first 12 terms happens to be 4095 over 4. Right, so there's your sum. Right, adding up those terms, which makes sense because I had some fractions, so I'm probably going to end up with not a whole number. So there's how we could use this a little bit, one of the applications of it. Think about example 2. Find the sum of, well, this series instead. So again, list out what you know. I know I've got the last term. The problem is I don't know what term it is. So I need to know how many terms it is in order to find the sum. So I need n here first. And again, this is geometric, because if you think about what you need to do to get from 4 to 12, well, you can add 8 or subtract 16. You could subtract 16, which is like adding a negative, but in order to get from 4 to minus 12, you'd have to add something. But the same thing doesn't work all the way down, right? The signs alternate, negatives and positives. So I know I'm going to be multiplying here. And that ratio, I can take my minus 12, divide it by 4. There's my common ratio of minus 3. So the ratio is minus 3, so this is geometric. T1 is equal to 4. I have Tn, which is negative 8,748. The issue is I don't know what term that is, so we got to find that first in order to find the sum of how many terms there are, in order to add them all up. So we can use our generic one, right? Our general term, Tn is equal to T1 Rn minus 1. I know the general term, negative 8,748. Is equal to your first term of 4, common ratio of minus 3, and then I've got an n minus 1 to deal with. So let's get rid of the 4 here first. So we'll do negative 8748, divide it by 4. So you end up with negative 2,187 equal to negative 3 n minus 1s, or with my exponent of n minus 1, I should say. But now, a little bit of guess and check comes into play. I can't really deal with that exponent without dealing with logarithms, and to do that I need some more math behind us. So let's think about what power of 3 will get us 2,187. So if you use a negative 3 as your base, put it to an exponent. 6 is not enough. It might be 7. It will get me that number. So I know that this negative 3 to the power of 7 will get me the same result. Now that I know that n minus 1 should be equal to 7. Therefore, n should be 8. So there are 8 terms in this sequence, and this last one is T8. Now that I know that, I can take the sum of these first 8 terms. So my sum formula comes into play now with my first term, r to the power n minus 1, and then r minus 1. I know I have 8 terms, so I'm going to add up all 8. So the sum of the first 8 terms, T1's 4. Ratio hasn't changed, it's minus 3. N's going to be 8 because I'm adding up 8 terms, minus 1. And then we'll divide this by the ratio minus 1. My ratio is negative 3 minus 1. So be careful with the signs. They cause a problem for a lot of people, especially with negatives. So the sum of your first 8 terms, 4. And then in brackets, let's do our negative 3. Right, so negative 3 to the power 8 minus 1. So 65/60. Whole thing divided by negative 4. Right, and it's negative 4 because I'm going to do negative 3 minus 1. Works out to be minus 4. The 4's will cancel. My negative will stay. So the sum of the first 8 terms is negative 6,560. Right, there's your sum. Okay, in order to use that sum formula, I just needed to know how many terms I had, which I could find using my general term formula. Okay, if you think about example 4, right, how many terms in this sequence or this series are required to yield a sum of, well, that's a big number, 35,872,265. So you're not going to sit there and add or multiply a bunch of times to get up to that number. That's just not efficient, right? We can be a little bit smarter about how we're going to approach this. So think about what kind of sequence this is. It doesn't say geometric or arithmetic, so in order to get from 5 to 15, multiply by 3, 15 to 45, also multiply by 3. So since I'm multiplying, I know it is geometric. My first term is 5, so I know those two things. And that is pretty much all that I know. I know what my sum is going to be also. So I know Sn is that 35,872,265. I know the sum of the first n terms is supposed to be that. I just don't know how many terms that is. So we are going to be looking for n here. So let's fill in some things. I know I've got a sum, and I know it's a geometric sum, so a series. So let's use our formula again. The sum of n terms is the first term, Rn minus 1, and then r minus 1 on the bottom. Fill in everything you know. So 35,872,265 equals our first term of 5. Ratio is 3. N is unknown. There's a minus 1. My r minus 1 is 3 minus 1. So let's simplify some things here. So 35,872,265 equals to 5, 3n minus 1 over 2. So that's 3 minus 1. So we'll get rid of our 2. We'll double both sides. So 35,872,265. Double it. So you get a real large number now. So 71744530 equals to 5, 3n minus 1. So divided by 5 to cancel out the 5 on the right side. So 143,48,906 equals to 3n minus 1. Add a 1 to both sides. 143,48,907 equals to 3 to the power n. Again, we're looking for that variable, which is an exponent. So you are going to do a little bit of guessing and checking, save you a bit of a time. 3 to the power 15 will be that number that we need. So there it is. They match. So 143,48,907 is equal to 3 to the power 15, which means I know n should be 15. Therefore, there are 15 terms, just by finding n. Okay, now the numbers can be quite big, again, for the reason being we don't really want to sit there and add things 15 times. Right? It's just not a good use of your time. We can be a little bit more sophisticated in how we find some things. A couple more. different contexts. So in a geometric series, the sum of the first 8 terms is 200. The sum of the first 9 terms is 800. What is the 9th term? And this one usually causes a bit of problem for people because of how simple it is. So think about this. If you've got 8 terms, right? So T1, T2, T3, T4, T5, T6, T7, T8, and here's T9, which is really what we're looking for. If you take the sum of the first 8, right? Take all those 8 and add them up. It's equal to 200. But then I'm also told that the sum of the first 9 is equal to 800. But that means there is a piece missing, the 9th term. So think about what you would have to add to 200 to get 800. It seems much more reasonable that way. The 9th term has to be 600. Didn't even need a formula, nothing. If you want to be a little bit more formal about it, the sum of the first 9 terms subtracted the sum of the first 8 terms will leave you with 600. Think about it that way too. Okay. Or the sum of 9 terms, the sum of the first 9 is going to be equal to the sum of 8 plus that extra term that is the 9th term. If you know that this is 800, you know that the sum of 8 is 200 plus the thing missing, well, 600 is going to be T9, right? Many ways you can think about it, but really it's just a subtraction question. Okay, that's all it is. There's one here that's an application, which is a little bit more complicated. We did one similar in the last video where we drew a picture out, so no difference here. Let's draw a picture. Right, so this ball is dropped from a height of 100 meters, bounces to 4/5 of its previous height on each bounce. What is the total vertical distance the ball has traveled when it hits the ground for the 8th time? So this height is 100 meters. Here's the ball. There it is. And we are going to drop it. Hits the ground, comes back up, and then goes down again, right? There's your first bounce. Hits the ground for the 8th time, so we need some bounces here, really, to get a picture for this. But essentially this is what happens. This is what's happening. So there's the first bounce, there's the second, third, fourth, 5th, 6th, 7th, and 8th. So I didn't really need to draw all of them, but I started, so I figured I'd complete the picture. So there we go. And we are told that it bounces to 4/5 of its previous height. So at the peak after that first bounce, we can take 100 and multiply it by 4/5. Essentially, it's 80% of what it was at. So after the first bounce, it only reaches 80, and then 80% of 80 to get the next one, so multiply that by 4/5, which is the same thing as 0.8, and you'll find that it's 64. And you can continue the pattern, but the total vertical distance is what we're looking for. Now, if it bounces, once it bounces, in yellow, it hits the ground, bounces up 80 meters. That is a vertical distance, but it also has to go back down. Right? It also travels that same 80-meter distance to go downward. So from the first bounce to the second, it's actually traveled a full 160 meters, 80 up, 80 down. So if you think about that the whole way through, even for the second bounce, it's coming down 64 meters, but it has to go up 64 meters in the first place. So there's 2 sides of this we need to think about. So highlight every direction going up in yellow, and everyone coming down in green, right? So there are all the vertical distances we have to account for. Now, the distances in yellow, all the ones going up, are equal to all the ones in green. So if I can find the ones in yellow, I'm just gonna double them to find out what the total is. So I know 80 only talks about 80 going up, how much it reaches after that first bounce. If I double it, I get my full total. So I can find out what the sum of those first 8 terms happens to be, that's a total, but I can only think about them either in yellow or green. Right? I don't really want to calculate the double heights for every bounce. So I can use a geometric sequence to represent this, and then I can add them up to make it a series. Once I get that sum, I'm going to double it to account for the fact that the ball also has to come down in green. Once I do that, I also have to remember that the ball even traveled 100 meters to start with. Right? Vertically, it had to drop 100 meters to get to the ground, so I have to add that in on the end as well. So what we're going to think about is our total distance, right? Our total vertical distance as being, well, the sum of the first 8 terms, but I'm going to double it, right? The first 8 terms can be represented as the yellow highlights or the green ones. Doesn't matter which one you choose, but I have to double it because that same height happens twice, and then I'm just going to add 100. Right? That's the piece that's missing for all of the total pieces here. So if I can find the sum of the first 8 terms, I'll double it and then add 100. That's the game plan. Okay, so the sum of the first, let's say n terms first, is t1, rn minus 1 over r minus 1. So I need some things. Well, I know that 80 is going to be t1 in this sequence. My ratio to get from one to the next, the thing you're going to multiply by, was 0.8. Right? That's 4/5. You can keep it as a fraction. You can turn it into a decimal. It does not make a difference whatsoever. So do whichever one you like. So we'll go find the sum of the first 8 terms. So the sum of 8 terms equals whatever t1 was, which was 80. The ratio 0.8. That exponent's going to be 8 as well for n. And then your ratio of 0.8 minus 1. Okay, so we can calculate the sum of 8 terms pretty nicely. So 80, if I do that 0.8 to the power of 8 minus 1, doesn't really look nice. But you can subtract them. You can put this all in your calculator. Maybe I'll do just that. I don't want to really write out all the decimals there. So what you will end up with is, well, let's plug it all in. So let's do 0.8 to the power of 8 minus 1, multiply it by 80, and then divide it by 0.8 minus 1. Okay, plugged everything in perfectly. I should have a positive. That makes sense because we're dealing with heights. It doesn't make sense if I had a negative. So we'll round this because it doesn't say where to round to, so we'll take parts of it. So we'll do 332.89, and those units are meters, right? So there's the sum of the first 8 terms. And now I can put it into what we said was our expression, so the total is going to be 2 multiplied by 332.89 meters plus 100, right? So our total is going to equal something, 332.89 plus 100. There we go. 765 meters, or 765.78 meters. There's the total, right? And that accounts for the upwards motion vertically, the downward motion vertically, and the extra 100 we had to account for. So it accounts for all of the pieces that we needed to. So there's a few examples on geometric series and some of the things we can do with it. So I hope that helps. In the next one, we'll start to talk about the infinite geometric series cases. What happens if it is not a finite series and it just keeps on going forever? So we'll get into that in the next one. Again, you'll find the links to all of those resources in the description box. Until next time, have a wonderful rest of your day.